So, welcome back. We have been looking at how to represent things in first order logic, and we have been gravitating towards this idea of creating abstract entities in the domain, so that we can describe the domain better. So, in the last session we created this entity called graph, which was a collection of nodes and relations between nodes, and we could talk about properties of the graph, that it is a connected graph. We could talk about other properties that graph theory people talk about essentially. Now, when we talk about, we are trying to describe the world, there are certain things we use in language which are not so easy to convert into first order logic. So, I might have mentioned at some point earlier that if you want to define the notion of tallness, if you want to say that Susan is tall, how do you define the semantics of that essentially? Of course, you can simply say that we have a category called tall, and if you belong to that category, then you are tall. If you do not belong to the category, you are not tall. But that would not really serve the purpose essentially. Let us talk about a simpler thing, which is to say if x is taller than y or x is heavier than y, then we would like to be able to compare them in some way and then come to a conclusion whether x is taller than y or not essentially. So, we already know of course how to do that. What we want to see is how to do that in first order logic. How would one say Aisha is taller than Sushma? One simple answer would be to introduce a predicate called taller and say Aisha 32 is taller than Sushma 29, or Aisha is taller than Sushma. The specific Aisha we are talking about is taller than the specific Sushma that we are talking about. But that would not help in reasoning except if you write rules explicitly using taller than. So, you could define, for example, the inverse relation, that if Aisha is taller than Sushma, then Sushma is shorter than Aisha. This kind of stuff you can do. Instead, we need a conceptual representation of the notion of tallness and being taller than. Being taller than is easier to define than defining what does tall mean, because as we might have said at some point, that it is a fuzzy concept essentially. As you, let us say, if you are a human being, as you inch towards 6 feet, you become more and more eligible to be called tall essentially. But there is no strict cutoff saying that above 6 feet you are tall and below 6 feet you are not tall, because you could be just close to 6 feet. And that is why Zadeh introduced this notion of fuzzy sets and fuzzy logic, in which one could talk in terms of such linguistic things. But let us get back to defining tallness, which is taller than, which is easier, because if we can measure their height, then at least we can say who is taller essentially. So, given the height of two persons, we should be able to decide whether the statement is true or not. We are trying to define how to establish the truth value of the statement, other than simply saying that we have this relation called taller and we will kind of populate it somehow manually or something like that. So, just a recap, we have been talking about aggregation, we have been talking of abstract entities and things like that. So, we have said earlier that when we talk about aggregation hierarchies, a bunch of things can be seen as another thing essentially. And we talked about abstraction also, but aggregation is what we are interested in here, and we saw an example of teams of sports persons, which is the example of a blue team from Italy from here. But that was one way of creating new elements in the domain by aggregation, saying that this whole thing is one element. This is a car. It is made up of 4 wheels and a steering wheel and whatever else is there in a car. So, we are talking about the process of reification. The reification is the process of adding abstract individuals to the domain. Now, we have been saying this ever since the beginning of the course, that in a way all our representations are reified, because human beings are after all a collection of 10 raised to 27 atoms or something like that. So, that kind of reification we have already accepted and said that yes, we will represent in our domain a human as an individual, as an entity in our this thing. So, even aggregations of persons, so teams we will accept as an entity in our domain. Now, we are talking about different kinds of abstract elements that are not aggregations, but new conceptual classes or types by themselves. And the kind of thing we have in mind is height, length, weight, color and so on. You might remember how we define the notion of natural numbers essentially. We created and said that this is a set of natural numbers which is part of our domain essentially. So, let us talk about height and tallness and things like that. So, we want to introduce something called a length type. So, a type is another word for category. It is a subset of the domain, but we are creating this new subset and adding it to the domain. So, let us call it the type length. This will include all elements that are of type length, whatever that is. We can access these elements by defining functions like length, height, distance and so on essentially. So, remember that a function maps its arguments onto some element in the domain essentially. Now, we are saying we have this new type of elements in the domain called length types, and we are defining functions which will take any other element in our domain and map it onto these length type things. So, we have not given names to them, but we are assuming that they are there in that. So, length pencil 71, it stands for the length of pencil 71, or if I talk about this pen here, this pen is an object in the domain, but its length is an element in that length type in the domain which we are defining. We are not giving that object a name, we are simply saying we will refer to it using this function called length. So, length of this pen will stand for that element in the domain which stands for its length essentially. So, that is an abstract type we are creating. We can do the same for height. For example, height and length are similar kind of entities. Distance, for example, between Chennai and Bangalore is also a length type. So, all these things will map onto those elements which are of length type. So, these 3 functions map their input to abstract objects of type length. So, the next question we want to ask is how do we quantify this length essentially. That is what we would like to do essentially. We want to be able to say that Aisha is taller than Sucheta or Shushma as the case was. To quantify these objects, we introduce units of measurements also as functions. Remember that functions are denotational in logic, in the sense when you say the president of the USA, it denotes a particular individual in the domain. Likewise, all other functions, mother of Sushma denotes a person who is the mother of Sushma and so on. So, here we have introduced this new abstract type called length, and we are defining functions which will denote objects in that type essentially. So, let us talk about feet. I do not know, we still talk about feet when we talk about measurement, especially when we talk about height of people. So, we can define a feet as a function to relate objects of type length, which is what we have just created by this process of reification, to numbers essentially, because eventually we want to quantify things. So, numbers we already know what are numbers. Now, we have this objects of type length, and we want to basically create a association between objects of type length and these things called numbers, which will help us quantify lengths or distances or heights as the case may be. We will talk about the type number here. We have not formally defined numbers, but you can imagine that it is not so hard. We have defined natural numbers, but let us include fractions here, which can be expressed in decimal form. So, you can define this function feet. So, remember now feet is a function. We are defining it as a function, and we can define it in two possible ways. One is that it is a function from the type length objects to the numbers. So, numbers we already know what are numbers. So, it takes an object of type length and returns a number to us essentially. So, you might say that the height of Aisha in feet is 5.9. That is what we want to say, and we can use it using this function feet that we have just defined, that takes an element of type length and maps it onto a number. So, what is the argument this sentence is saying? The argument to feet is the height of Aisha 32. We have already said that this height is a function which maps Aisha onto some object of type length. Now, we are taking that object of type length and saying we are using another function feet to map it onto a number, and the number happens to be 5.9. So, we will interpret this as the height of Aisha is 5.9 feet essentially. That is one way of defining the feet function. We can define it in the opposite direction also as well. We can say that feet is a function from numbers to objects of type length. So, which means we can abstractly talk about 5 feet. What is 5 feet? 5 feet corresponds to a certain type, some object of type length essentially. So, this definition takes a number as an argument, and represents the number in feet, which means it translates it into a particular object in that length type. So, you can imagine that all objects of same length will map onto the same object essentially, and that object could be, for example, 5.9 feet essentially. So, height of Aisha maps it into an object of length type. Feet of 5.9 in this new definition also maps it to an object, and we are saying that they are the same object, that whatever we mean by 5.9 feet is what we mean by the height of Aisha essentially. So, these are two different ways of defining a function called feet, which can now be used to talk about properties like height and length and distance and so on. So, we were interested in being the taller than properties. So, let us look at that. So, we define feet as two kind of functions. In one type, when we map from length to a number, we can say that x is taller than y for all x y if there exist two numbers n and m, such that n is the height of x in feet and m is the height of y in feet, and n is greater than m. Then we know that x is taller than y. We can do this in the other definition as well. If you are moving from numbers to length, then again we are saying that x is taller than y if there exist two numbers n and m, such that when you express n in feet, it is equal to the height of x, and when you express m in feet, it is equal to the height of y. These height are these type of length numbers, type length objects, and we also know that n is greater than m essentially. So, in both definitions you can define the notion of tallness. Once we treat this function which goes from number to length, for example, feet, 5 feet, 6 or 5 feet or 6 feet, we can define an ordering between them. We can say 6 feet is greater than 5 feet essentially, because 6 is greater than 5 essentially. Then maybe we do not have to go to numbers, simply to say which one is higher in the ordering. How does one deal with mixed units? So, we do not often deal with only one kind of units. You must have spent a lot of time in school working with mixed units. So, for example, instead of saying 5.9 feet, we are saying 5 feet 9 inches, which is of course different from 5 foot 9 feet. But how do we handle things like mixed units? So, here is a small problem. So, one thing one could do as a project is write a program to read word problems from high school maths or high school physics and then solve them using logic or whatever other forms of computation that you can use, including addition, solving equations or whatever the case may be. So, you read problems in English. So, of course, you need to have this NLP component. Express then in some logical form, which includes mathematical notation. Use a method to solve it and produce the answer. And if you kind of worked on a small well defined domain, you could have a program which could solve problems of those kind. For example, chapter 6 in class 4 maths book or something like that, and you could build a teaching system which will help students to solve word problems in maths or English and so on, not English, in maths and physics. So, this could be one such problem which some student would have had to solve, that Swami jogged for 3 kilometers and walked for 500 meters. Then he stopped by for a cup of tea, and then he walked for another 600 meters and jogged for 2 kilometers. What was the total distance he covered essentially? These kind of problems can be solved in logic, and we know that logic subsumes mathematics. So, one way would be to define an algorithm to solve mixed units, just as we have learned how to solve addition in school, that you first add the units, then you add the tens, then you add the hundreds and so on, and then keep carrying over. We could do something very similar. Here we say first we add the meters, then we add the kilometers and so on essentially. So, then you would have a process which is something like this. You want to add these two objects of type length. So, first you add 500 and 600 and you get 100 plus a carry of 1, because what you get is 1100, but that 1 goes as a carry essentially. So, there would have been 1100 out of this 100 comes here and 1 is the carry. So, this carry comes here and you add it to the other two, 3 plus 2 plus 1, you get 6, and the answer is 6 kilometers and 100 meters. Another way would be to convert everything into one unit, and then of course, you can add and subtract and this thing. So, people say you can't compare oranges with apples. So, you can't compare kilometers with meters. But if you convert everything into meters or you convert everything into kilometers, then you can jolly well add and subtract and do whatever you want. And we can write such conversion definitions. So, here we are saying that for all numbers n, if n is being measured in kilometers or it represents a length in kilometers, then it is equal to, if you multiply n by 1000, the same length in meters essentially. So, you can convert from kilometers to meters and meters to kilometers. In the other definition also you can do that. You can say that if you have the height of x in feet, remember this will give you a number, and if you have the defined height of x in inches. So, if you have the height of x in inches, then if you multiply it by 12, you will get the height of x in feet. So, you can do conversion essentially, and then you can solve these kind of word problems. Let us just talk about colors a little bit. We will not go into too much detail here. So, two possibilities occur, just as we said that when we talk about taller than, we can just simply define the predicate that x is taller than y, but then we have to worry about how to populate it in the knowledge base. Here also we can define red as a category, and we can say, for example, that ball 33 is red essentially. How did it go into that category is something that you have to address. We can think of red as an abstract object, just like we talk about length as an abstract object, we can talk of color also as an object. So, we can have something of a type color, and then red maps onto that element in that type essentially, and we have given it a name that it is called red. So, red is an abstract type, and this color is a function which maps this ball onto this abstract object called red essentially. Remember that these two are similar definitions. I think we are defining a predicate there, that there is a color predicate which kind of connects ball 33 with this object called red essentially. One way I often want to say that, how do you define similar colors? So, I might tell you, for example, I might give you my office keys and say, go and pick up this book on logic from my shelf. It is a green colored book, but it really depends on how you interpret green essentially, because there are so many variations, parrot green and Prussian blue also looks like green and so on. So, if we have an understanding that when I say green, then I mean also something very similar to green, then we would have a working relation there, and you could find that book essentially. But how does one define similarity in colors essentially? So, as you probably know that colors can be represented using their red, blue, green coordinates. So, every color can be expressed as a weighted sum of these three colors, red, green and blue. We could use those values, how much red is there, how much green is there, how much blue is there, and if we take two colors, then we can think of it as a distance between these two points in 3-dimensional space. One is red, one is green, one is blue, and then you measure the distance between them. That would be a distance between those two colors. So, red minus red whole square and so on essentially. And then we can normalize it to 0 and 1. All distances, maximum distance is 1, the minimum distance is 0 essentially. And similarity can simply be defined by saying 1 minus distance. Once you have normalized it to 0 and 1, it will be between 0 and 1. So, similarity also will be between 0 and 1. Then you can give a number to what is the similarity between red and maroon. Maybe it is 0.8, maybe it is 0.7, I do not know, but some such number you would get, and then you could define something called a predicate, which is actually a fuzzy predicate, but you can define it using a threshold essentially. We say that two colors are similar if the similarity value between the two is beyond a certain threshold. So, if it is more than 0.7 they are similar, if they, or you might say if more than 0.8 they are similar, but we can do that essentially here. So, color is also something that we want to think of as abstract objects, just like we did about numbers and length and so on essentially. We would be looking at more abstract objects. This process of reification is not over yet, but we will do that later, and we will then talk about relations of arity greater than 2. So far we have talked about unary predicates, which are categories and properties. We have talked about binary predicates or binary relations which connect two elements together. What about predicates which talk of more than two arguments? We will see that this reification would be a useful tool to work with there as well, but we will take that up in the next session.